Alright, the screencast is kind of a happy and a sad tale. And it's going to be the life and death of a photon. The photons are born, they struggle into existence, they have to make a mighty trek, and then are observed and forgotten almost instantly. So to begin this tale, we got to start off in the core of a star. And we're going to be looking at how we can look at what's called thermonuclear fusion. How hydrogen and hydrogen are, let's just say, heated and compressed together, and they begin to form new elements. But it's not this one hydrogen, it's actually more complicated than that. It takes 4 hydrogen atoms to go through a process called the proton-proton chain. In this process, new elements are made, and a tremendous amount of energy is released. This takes place in the core of all stars. Since Einstein proved to us that energy equals mass times the speed of light squared, we can actually apply this concept to how matter is converted into energy that we see as sunlight. Then we can do some simple math here, looking at how 4 hydrogen atoms are fused into creating helium through the proton-proton chain reaction that takes place in the core of all stars. So let's look at hydrogen. It's atom number 1. It has an atomic mass of 1.008. It takes 4 hydrogen to create 1 helium. But the numbers do not add up. This is because 4 times 1.008 equals 4.032. But helium, atom number 2, the atomic mass of 4.003, well, let's just say that doesn't equal 4.032. The missing mass is actually the conversion into pure energy that we see as sunlight. Now, I would encourage you to check out these videos here. Here's what I'm showing you. 4 hydrogen, and there's a little bit of a more complex reaction that takes place because a proton has to be changed into a neutron. But let's just go with this for a minute. That 4 hydrogen can create 1 helium in a tremendous amount of energy. Tiny amounts of matter or mass can be converted into tremendous amounts of energy. See for yourself. So watch this video and then watch this video. And that'll give you a little bit more insight as to what's taking place there. So voila, light is born. So all of a sudden now we have the electromagnetic spectrum. We have this pure energy that's formed. But it's not as simple as that. The dual nature of light. Light can be both a particle and a wave. If light is imagined as a flow of particles, the particles called photons, with each photon carrying a discrete packet of energy. As a particle, these photons carry momentum, yet they have no mass. So light can be described as waves, with characteristic wavelengths and frequencies that are inversely related, where we say that c is the speed of light equals the frequency times the wavelength. And if I look at the electromagnetic spectrum, I simply see that my frequencies down here at the gamma end are much, much higher frequency, higher energy, much, much smaller wavelength. Where at my radio end, very, very low frequency, very, very large wavelength. And I can apply that to the visible light spectrum. Here I have the Roy G. Biv spectrum. Notice that the blue-violet end is the higher frequency, higher energy, and the red and the orange end of the spectrum are the longer wavelength, the smaller energy, lower frequency. So light behaves in what's called a duality, where the observer can view a photon or light as either a particle or a wave. And we can apply this concept to solar sails. We can look at light as a particle. We can say light has momentum. And a solar sail is actually how we can use spacecraft and we can move it. If we view sunlight as if it's a particle, here's what's happening to drive the solar sail. The incoming photon strikes the surface of the sail and it bounces off. It imparts its momentum onto the sail. As continued photons strike the sail, more and more momentum is transferred to the object with the sail. And we can actually use sunlight to do work simply by applying this physics. So we're using sunlight and the momentum here to then change the momenta of the object that we have the sails put on. So here we can view light as a wave, and this is where the characteristic wavelength and frequency comes into play. But we need to make sure we realize that red photons will always have this distinctive large wavelength, low frequency, and a blue photon will always have a characteristic higher frequency, smaller wavelength. So now we have this photon, and it's just been formed and just been created from the conversion of matter inside the star. So photons are born within stars, including our sun, as hydrogen is bound into helium, creating a high mass element. Photons are the byproducts of nuclear fusion. And Einstein showed us that energy equals mass times the speed of light squared. It says that he showed us that these are really just the same thing. That the total matter in equals the total matter out plus the change in energy. It's pretty crazy how that works out. But it's not that simple. That photon has just been liberated from its matter form, but now it has to get out. It has to get out of the sun. So once the nuclear fusion process takes place and photons are generated from the matter, then it must migrate out of the sun. This is called the random walk, and sometimes it's referred to as the drunkard walk. This theory explains how this is done. As a photon attempts its escape, it must collide with matter on its way out of the sun's interior. So it must be absorbed and re-emitted each and every step along the way. It's going to be absorbed and re-emitted every time it comes into contact with a very, very high dense material. So it's going to take a little while. So here it says the random walk. So here's the storyline with the random walk problem, because it's not this linear process that you might think of. In order to figure out how much time it takes for a photon to be born at the sun's core and escape, you must first take into account some information. Once you know the typical distance between collisions, you must also figure out how many steps the photon has to take to travel from the core to the sun's surface. If you take a sequence of n random steps, each step we can say is 1 meter in length. The distance you must travel from the starting point will be the square root of n. After 100 random steps, you will travel about 10 meters, but it will take 10,000 steps to travel 100 meters, and 1 million steps to travel about 1 kilometer, and so on. So the density of the interior of the sun is more like a collection of shells of matter, each with its own average density. You must then calculate how many steps it takes for a photon to travel through each shell, all while the photon travels the speed of light, gets absorbed, and then re-emitted each step along the way. So you can calculate the time required by each step and multiply this times the number of steps. Therefore, you can calculate the time for a photon to traverse the sun and leave it. When this random walk process is applied to the interior of the sun, the answer comes out to be between 10 and 170,000 years. And I've seen 170,000 years as kind of the more accepted value. So here we can do some calculations of the speed of light. The speed of light is roughly 186,000 miles per second, which is about 300,000 kilometers per second. Earth's average distance from the sun is 93 million miles, and from the moon is 240,000 miles. So how long does it take the Earth to reach the Earth from the sun, and then how long does it take to reflect from the moon to our eyes? So you can do these calculations. You can do the calculation for how much time it takes the sun to travel to us in seconds and in minutes, and how much time does it take light to reflect off the moon and reach our eyes. Then I'm going to have you do some calculations here with AUs. 1 astronomical unit is 93 million miles, the average position of the Earth-Sun. And this is a reference of this mean distance. You'll calculate the distance in miles and the time for the photon from the sun to reach the following. The distances, remember you'll have to take these times 93 million miles, and you'll need to calculate the time in which it took for those photons to travel. So let's take this a little bit further. Let's talk about a light year. A light year is the distance that light travels in 1 year. It is equal to 9.46 times 10 to the 12 kilometers. Alpha Centauri, A and B are roughly 4.35 light years away from us. Proxima Centauri is slightly closer at 4.2 light years. So show your work how you can calculate how far a photon travels in 1 year. And then I'm going to have you calculate the closest star is the red giant called Proxima Centauri and is located 4.2 light years away. How many miles away is that, and how many AUs is that? The closest galaxy to our Milky Way galaxy is called the Andromeda Galaxy, and it is located 2.2 million light years away, or light years from Earth. It is traveling toward the Milky Way galaxy at about 670,000 miles per hour. How many miles away is the Andromeda Galaxy? How many AUs is the Andromeda Galaxy? So the galaxies, our Milky Way galaxy versus the Andromeda Galaxy, they're on a collision course. Our Milky Way is on a collision course with the nearest galaxy, the Andromeda, and the two galaxy trajectories intersect in about 5 billion years. So if stars are so bright and galaxies are filled with them, why can't we see them very well? Well, the short answer is they're so far away, they aren't very bright. So we can look at apply the concept of the inverse square law to make sense of this. Light appears less bright, or less luminous, the further the observer is from the light source. Now we talked about anything that's emitting light. We can say a light bulb or a sun, a star. That these are emitting light, that the rays coming out represent photons, the pure energy, that's the light, traveling in straight lines. But as one moves further from the source, the intensity of light appears to decrease. Intensity decreases based on the inverse square law. As one increases the distance from the source, the apparent luminosity, which is the value of intensity, decreases by its inverse square. So if I have a value at 1 meter of, let's just say, 1 watt per meter squared, if I'm twice as far, it's only going to have 1/4 the value at 1 meter. And so on. I'm taking this by the inverse square. So if it's twice as far, it's going to be 1/4 the intensity. If it's 3 times as far, notice the 1 meter, this value here is our reference. If it's 3 times further, 3 meters away, it's going to have 1/9 the total intensity. And 4 times further, it's going to be 1/16 the intensity. And if it's 10 times further, it's going to have 1/100 the intensity. So we can start looking at this picture right here and say, okay, well, the further it gets, it's going to have less intensity by an inverse square. So let's look at this a little further. Intensity is going to equal 1 over distance squared. The further one is from the light source, the intensity in watts per meter squared decreases by its inverse square. A watt is a measurement of power, or the amount of energy that something generates or uses over time. So here's another picture. If the intensity at 1 meter, at this distance right here, is 1 meter by 1 meter, so 1 meter squared. If the intensity at this location is 8 watts per meter squared, we would say that at this location, this would be twice the distance away. It's going to have 1/4 the total intensity. Oh, here we go. Here are my values. This is what I'm looking for. If I have 8 watts per meter squared at this distance, 1 meter, at 2 meter distance, I'm only going to have 1/4 the intensity. And I can see this. Its value is going to be 2 watts per meter squared. So I can apply that concept to not only sunlight on the Earth's surface, right? Light intensity of 500 watts per meter squared at this area. But in all intent and purposes, we actually get a regularly, kind of a fairly consistent amount of heat energy from the sun. We're simply looking at stars that are tremendous distances away. So I'm going to have you can go ahead and pause this and do these calculations and walk through what's in red. I solved them for you because we're still telling the story of the photon. So once that photon travels through space at the speed of light and it makes its way to us, it then reaches our atmosphere where it then refracts. Refraction is the bending of light rays. The ability for a material to bend rays of light is described by a value called the index of refraction. And it travels from the vacuum of space into our atmosphere with air. The air has an end value of 1.0001. So refraction occurs when light rays cross a surface between two materials that have different index of refraction. So once light travels from the vacuum of space into our atmosphere, it must refract. They have different end values. And as a result of this refraction, it's going to actually refract a couple different ways. The photons that have successfully made the 93 million mile trek through space arrive in our atmosphere. At this point, they refract. They actually slow down. And the entry into the Earth's atmosphere is the new medium which the photon has to travel to. So it refracts as it slows down. The change in speed is because it has to be absorbed and re-emitted from atmospheric molecules, the gases. That the speed of light changes from 3 times 10 to the 8 meters per second to 299,970 meters per second. So only slightly. It's still crazy fast. So moving on here, let's look at this. So how would I solve? So I want you to pause this and read this because I'm going to talk you through how to go ahead and solve that. But it is important that we realize that refraction is really just the slowing down of a material based on its end value. So now we've got light entering our atmosphere, and we see refraction in colors of light. That the index of refraction for almost all materials varies by a small amount depending on the color of the light. So here we can actually have white light that gets refracted through a prism that gets separated into colors, and this is called dispersion. And we can actually have blue skies, right? Our blue sky is the result of what's called scattering. And we have red sunrises and sunsets for a different reason. Blue skies, and you can read about this here because I'm about out of time. Blue skies are simply the result of scattering light, and short wavelengths are more visible or just scattered more effectively or readily than that of other colors. So blue is the last one observed. And at the end of the day, those photons somehow make their way into your classroom and reflect off of something, make it to your eyes, and this is where the rest of your eyes and